Well, why don't you talk from there? Is that, oh, that's not being broadcast.
Yeah, no, sorry, I just want to give you a second to get it.
My map is not seeing it. Windows machine. Okay, can I give it to you, Lola?
And then send it to,
You want to put it on the Twiki? Or you want to send it, I'll tell you who's on, and you can just send it to them if you want. It's Arpita, Jimmy Chen,
send
Narayan.
it to Prakal.
Sure.
I mean, Peter just has to walk over, right?
Why don't you go ahead and then please start talking.
All right.
Let's do it.
Oh, okay. Thanks for having me here. It's certainly fun to come here to talk at Yahoo. In fact, I've given a couple of talks in the past, and so today I'm going to talk a little bit more about the kind of things I would like to do in the future. So there's some work in here that is kind of looking back at research that I have done, but there's actually a good bit in there too that's talking about research we're trying to do right now, and I would really like to kind of stir a little bit of discussion and get your input on some of these things, because this talk is, well, you know, the main focus of my work on the theory side is certainly machine learning and optimization, but this talk is more towards the application side, mainly towards the application that has been inspiring me for about 5-6 years now, which is music search and recommendation. And so today what I would like to focus on more is really like how can we personalize it, how can we kind of bring it on mobile devices in ways that it actually serves us with content that we are interested in at a certain time in a certain place. Okay. So basically, I guess you guys probably have seen this type of picture before. I mean, in the past 10-20 years, there's been a lot of music content that made its way to the internet because of, you know, more easy production. You can basically build a music studio if you want in your garage nowadays. And because very easy distribution as well. People just upload it online and then download it on the other side of the world in a matter of minutes. So there's quite a few services out there nowadays that have databases in the order of millions and tens of millions. And so those are certainly, you know, pretty decent numbers that will require, you know, some technology to bring content to the user. For example, if you compare this with Netflix, which has a database which is really in order of magnitude smaller here. And so the idea really of a lot of the work that we've been doing in the past 5-6 years is really how can we bring you know, the right music from this really big pool of music that's available online to, you know, the devices of the user, which, you know, are smartphones, iPods, etc., etc. And so we would like to do this in a way that the user doesn't necessarily need to know an artist name or a song title all the time. So the question is really like, how can we help a user that, for example, is looking for, you know, some music for rock and roll for working out in the gym, or you know, some romantic music when coming home with a date, or some scary Halloween music on October 31st, without knowing an artist name or a song title. That's really the idea here. Right? And going one step further, maybe even better would be some kind of zero-click setting where you know, you don't even ask the user what they're feeling like, but somehow the mobile device of the user figures out that they're in the gym now, and therefore would like to listen to rock and roll and starts playing some rock and roll music. So that's kind of like the idea. So how do we bring content from this big pool of music that's out there to the user in a way that is as user-friendly as possible? Now, in order to kind of solve this problem, like let's assume that the user provides us with a description of what they would like to listen for example, happy rock and roll or romantic jazz, right? If we'd like to build an engine that then helps out the user to find the right music from this big pool of possibilities, in order to do that, the kind of engine or black box that we would need is a music auto tagger. It's basically like machinery, an algorithm that, you know, given an audio waveform, is able to tag that audio waveform with tags such as romantic, jazz, drums, guitar, etc., right? Because if we can build a black box that indeed can tag music with tags as diverse as genre tags, moods, instruments, or usage tags, then we can actually use that to build an index database of annotated music. Right? Because the way this would work is that you feed basically a waveform of a certain song into the algorithm, and then the algorithm will output the tags that are most applicable for that song. And what's important is that the algorithm would only use the waveform here. So this is also applicable for songs that are very or relatively unknown, for which the only information that we have available is that waveform. Because of course for more popular music, very often you have all of metadata available, from which it's usually very easy to derive that it's actually rock and roll or trance music or things like that. Okay. And so just to give you an example here, this is an example of, oops. So this is an example of a song.
Fly me to the moon, let me play.
We feed into our algorithm, so to speak, and what the computer then can do is it can predict the most applicable tags, which here in this case are fit into
Your line has been muted.
Oops. No, we're trying to put a presenter back.
So here in the gray text, what you see is basically just kind of like a standard sentence, and then what we do is we substitute in this sentence, you know, the most likely genre words. The most
Your
likely
line has been
words,
unmuted.
the most likely instrument words and things like that, and so that way you can actually kind of come up with a short description of the music. So this is like kind of like the robot review of the song. And so if you look at this description here, given the song that you just heard, it actually makes sense that this is a calming or sad song, that it's rather slow tempo. Sometimes there is, you know, some kind of mistakes that the algorithm will make. For example, if you listen to this song here, then you can certainly agree that this is dance, poppy, hip-hop type song, but sometimes it makes a couple mistakes, like for example, it's going to predict an acoustic guitar solo here, while hip-hop music, I haven't really heard that very often, honestly. But you know, in general, it's pretty clear that, you know, this description certainly goes with this song here, and this type of description goes with that song. And so basically the end result of this really is that, you know, we can feed audio waveforms through a computer algorithm, and as a result we get, you know, tags that are highly descriptive of the song, and now you can do this for any, you know, very large database of songs. And so as a result what you get is an indexed database which can then be used to, you know, help the user, that provides you, for example, with a semantic query by simply matching the words in the query against the tags in your database, and, you know, as a result you generate some kind of, you know, list of recommended music or a playlist or something like that at a radio station. You could also use this with a seed song. So let's say that, you know, the user provides you with a song that they actually like, and they would like to retrieve more similar songs from that database. Then what you can do is you can just retrieve songs with similar tags from this database and generate a playlist in that way, which is kind of like what Pandora does. But the difference with Pandora really is that, you know, if you're going to query Pandora, you really have to start with an artist name or a song title. You can't really say, give me some, you know, romantic jazz music, unless if they have some, you know, pre-generated romantic jazz radio stations. But if you come up with like some kind of more crazy queries, like, you know, party music with a horn section and stuff like that, you can't really find that type of music on Pandora. The other thing also is that the library of Pandora is fairly limited. It's probably around 1 million songs right now. And the reason for that is that the way for them to add songs to their database is by manually indexing them, and not, you know, automatically using computer algorithms. Genius is another service that's out there that actually allows you to provide a seed song, and then, you know, we provide you with similar music, but most of that algorithm is based on collaborative filtering type data in terms of, you know, their sales records, in terms of, you know, playlists that their users have and things like that. If you feed Genius with like a song that you just recorded in your garage, then it's going to give you an error message most of the time and tell you that it couldn't find any similar music. So the system that I just presented here actually kind of overcomes some of these restrictions. I mean, it allows us to search by any type of query. It allows us to seed it with songs that you just recorded in your garage, and we'll be able to come up with similar songs simply because the only thing we need to process a song and add it to our database is the MP3, the waveform. We feed the waveform to the algorithms, and then those algorithms will automatically tag that waveform and add it to the database. At some point in time, a couple of years ago, we also compared these two systems actually for playlist generation. So what we did is we did an anonymous playlist survey, and it actually turns out that the playlist generated by the Genius system and this automatic tagging system are actually voted fairly competitive by users. So that was actually some really good news because, again, as I said, Genius can't really mind the long tail of music. Very obscure, unpopular music is really something that Genius can't deal with very well. And so then one more thing to add here as well is that, of course, when you're talking about music, for long-tail music, maybe there's only audio waveforms available, but once you kind of like go into a little bit more popular music of bands that have, you know, more extensive websites, and very often there's actually much more information than just the audio waveform available about the music. So you can have lyrics information available, there may be author biographies, there may be blog posts, videos, pictures, and things like that, collaborative filtering information. So we may have a lot of extra information available about the music, and so one of the things that we're looking as well at in Cal Lab is how we can integrate this information with the audio waveforms to improve recommendations. Okay? I'm not really going to talk too much about this today, but if you're interested in how to really like process this more rich type of sets of multimedia data, this is certainly something that we can talk about offline afterwards. So what I'm going to focus on here is really how do we build a tagger, how do we automatically tag a waveform or an MP3, right? So basically we're going to do that using signal processing and machine learning, basically taking the traditional machine learning approach where we collect a bunch of training examples. So for example, we collect a set of rock songs, let's say 1,000 rock songs, and then we're going to try to identify which typical audio waveform patterns are shared between all these songs, and then take that as a typical pattern that characterizes rock songs. And then, you know, if we recognize a similar pattern in any unseen music in the future, we'll tag the song with rock. Now, how do we do that? So how do we build these type of models? I mean, there's a variety of work has been done on this in the past 4 to 5 years. The approach that we took is we took a generative approach where we're basically going to try to model the distribution of audio content for each given tag in our vocabulary. Right? So basically what we're going to do is we're going to have a setting where we assume that we're given, let's say, 100 or 1,000 songs that are associated with a certain tag, like with the tag rock, and then we're going to estimate the distribution of the audio content X for that tag T, rock here in this case. So more specifically, let's forget about tag level modeling for a second, but let's just look at a single song. So how do we do this? Well, the way we do this is we take this audio waveform, we're going to chop it into little pieces, most of the time something like 50 milliseconds long. From each little piece of the waveform, we're going to extract some features, which there's a variety of features, but some of the popular features nowadays are these MFCC features with their first and second order derivatives. So we extract features from this 50 millisecond segment and we represent this in some high dimensional feature space here. And then so basically what that does is it represents this waveform as like a cloud of point in a high dimensional space. And then in the next step we're going to try to somehow fit a probabilistic model to this audio content here. For example, a Gaussian mixture model or some other type of model, right? Using some type of estimation algorithm like EM. Okay, so that's kind of like the idea. In order to model a tag, you can actually do the same thing. So now what we want to do is we want to build a model for a typical audio content for the tag rock, let's say. So what we're going to do is we're going to collect, let's say, 1,000 rock songs. Each of these rock songs can be represented by this cloud of feature vectors. We're going to merge these feature vectors all together. So now this is somehow like, the cloud that characterizes the tag rock, and we're going to model that cloud with a statistical model of audio content for the tag rock. Okay? Of course, doing this computationally could be very expensive, since this could be a space with a lot of data points here. So we've developed algorithms to do this more efficiently. I'm not going to go into detail about that today, but that's certainly some bit of machine learning work that needs to be done here. And so then once you have these such a model for rock, you can develop similar models for other tags like mellow, romantic, and hip hop. And so then when you're given a new song that the system has never seen before, you do the same thing. You chop it into pieces. You represent it as a cloud of feature vectors, and then you're going to look at which of these tag models is most likely to have generated this cloud of audio content, and then based on that you will tag the song. Or vice versa, you can just look at like what is the probability that this cloud of feature vectors was generated by a mellow song, and then given that likelihood, you can then assign a certain weight to the tag mellow for your song.
There's just one thing, the prediction is done for each frame separately, right? In the
The
test.
prediction, okay, good question. The prediction is actually, this prediction here is done for the entire song, so you're kind of like combining all the frame-based information. So you basically come up with one semantic multinomial of information. So for example, let's say if we have the song Give It Away from the Red Hot Chili Peppers, you feed it through the system, and basically as a result what you get is, along the horizontal axis here is our dictionary of words, which are in different categories. Like here is a bunch of emotion words, genre words, instrument words, usage words like, you know, exercising, running, sleeping, stuff like that, and vocal characteristics. And then along the y-axis, you see how relevant the algorithm judges that tag is for that particular song. Okay. Now, one thing that's important to keep in mind here is that this approach that I presented so far, what it does is it basically chops the waveform into these 50 milliseconds frames here, and then represents each frame as a point in this high-dimensional space, which can be considered as an independent sample of the statistical model that we're generating here. So what that means is that if we just randomly permute the order of these 50 millisecond frames here, like this, for example, then in terms of the representation here, nothing changes, and in terms of the model, whatever we obtain here is still equally likely to be sampled from this model here, but if you would listen to it, it would basically just sound like nothing, right? Like noise. So clearly, like when we build a model in this way here, there is somehow something we're not capturing. What we're not capturing here is really kind of like the time dependence between these 50 millisecond segments. So in order to try to take that into account, what we're going to do is we're going to glue a bunch of these 50 millisecond segments together into a sequence, like for example, 500 or 1,000 of them, we're going to glue them together into a 5 to 10 second sequence of audio content. And we're going to then model that sequence as a sample from a linear dynamic system, or a Kalman filter. People call it dynamic texture in computer vision. So basically the model we're using here consists of a hidden variable which characterizes the temporal dynamics of the signal, and it consists of an observation variable for each of my hidden variables, which describes the instantaneous spectral characteristics of each of these short 50 millisecond segments here, right? And the hidden variable evolves according to a linear equation. In this case, is a continuous variable, as opposed to, for example, hidden Markov models where this would be a discrete variable. Hidden Markov models are often used for speech because there is kind of like this underlying assumption that speech is basically a series of phonemes. But for music, it wasn't so obvious to us that there's actually something like musical phonemes, and so therefore we opted for a continuous hidden state model here. Okay, so when you do this, there's still one more problem, which is that if you're trying to model a single song, it's unlikely that every 10-second segment from this song can be considered as a sample from one and the same dynamic model, right? Because you can have a guitar solo, an intro, an outro, a verse, or a chorus. And so therefore what we do is we're going to model songs as mixtures of these dynamic textures. So we're going to allow different type of dynamic behaviors to be present within one song. So basically what that looks like then is that if this is a song here, let's say 2 minutes of audio or 3 minutes of audio, then basically then this song is going to be modeled by a mixture model where now the mixture components are not Gaussians, but each mixture component here is basically a Kalman filter, linear dynamic system, right? And every 10-second segment from the song is a sample from mostly one of these mixture components, right? So for example, here in the beginning of the song, most of these 10-second segments are samples from the green mixture component. Further down the song, most of these 10-second segments are samples from this blue mixture component, which is a different temporal dynamic behavior, right? And what's interesting is if you just take a song without any further information, just the waveform, and you fit this mixture model to the song, then by doing what I just did and assigning every 10-second segment to the most likely mixture component that generated it, you actually automatically generate a segmentation of the song after a little bit of low-pass filtering around the edges here. It works out pretty well, actually. So anyway, so that's basically an approach that allows us to take this kind of temporal, this time series character of music into account. It allows us to do song segmentation. It also allows us to use this model for tag modeling in a similar way as what it said before. Basically, instead of now modeling one song, we model a whole set of songs. And then given that set of songs, which could be like 1,000 examples of electric guitar songs here in this case, we will now try to figure out what are the most common or the most dominant linear dynamic behaviors in these songs. But the problem is, in order to fit this model again, it's kind of like fairly challenging with all the data we have here. So what we do is we take a hierarchical approach where we first fit song models. So for each model we will fit a mixture model of Kalman filters, and then somehow with the next hierarchical step we will try to identify what are the most dominant dynamic behaviors that we can identify amongst these models here into the final tag model. Okay, but so the bottom line here is that by going from these Gaussian mixture models to dynamic texture mixtures, we're taking into account the time series behavior of music. And so if we do an experiment after collecting a bunch of training examples, by the way, talking about collecting training examples, this is another kind of challenging thing that we encountered by being in this music space. Especially like about 5-6 years ago, there was no training data. There was some training data. Pandora had a bunch of annotated music, but they wouldn't share it. So what we did instead is we set up our own little mini Pandora in the lab and set up a survey that we had undergraduate students from the music department fill out. And so as a result of that, we actually were able to collect a data set of about 500 songs that are annotated with about 200 tags. And so based on that data set, we did a couple experiments where we would train on a subset of the data and then test the precision at 10 on a test set. And as it turns out, using the Gaussian mixture models, we would get a certain performance, but then using these dynamic texture mixtures, we would actually get about a 15% boost in performance by using these better models. Okay, so it does make a difference to share to use these mixtures of in the dynamic systems. Anyway, so this is kind of like a little bit of a quick look under the hood of this automatic tagging algorithm. One of the things that Pat was mentioning earlier was this herded game in Facebook that we developed, and that game actually got developed as a result of trying to develop these algorithms, because as I said, like trying to get training data was a hard process, and trying to get it from undergraduate students was possible. It gave us good data, but there's a certain limitation there in terms of how much you can pay to collect the data in terms of scalability. So instead, what we decided then is to collect more data, not by using human surveys, but instead by developing an online music game on Facebook. And basically the idea here is basically the typical crowdsourcing human computation idea. So you try to create something that people will go to and will play, so to have fun for them. But at the same time, you hope to collect data from that game on the back end that you can then use for whatever purpose you want. In this case, training data for our machine learning algorithms. And so the idea here is people are all like in one room in a Facebook application, so they're all in the same room listening to the same song, which is playing here, through the timer on the top of the screen. And so while the music is playing, they see several games presented to them. It could be like a game where they have to make a yes/no decision, whether the song has good lyrics or not. Sometimes we throw in some random questions that don't really give us much information, but just because people kind of like to play around with it. And then after people click on a certain answer, what you get is that they see what the other people in the room voted on. And based on the agreement with other people in the room, a given person can then gain more or less points. Okay, so that's kind of like the idea here, and then there's some little trivia rounds that we put in the middle as well, just to keep people entertained. But the bottom line here really is like it's an online, real-time, game on Facebook that is meant to entertain people, have them click on tags for music, and at the same time, like for example, here's a game where we present all the users with 9 genres. They're listening to a song and they have to click on the genre they think is most applicable. And then once the timer runs out here, you actually see again what other people voted on. And so you see how many people agree with you or not, and depending on that again, you get a certain amount of points.
Do you have access to the data?
Yeah, so we have access to it. I mean, it goes straight to our server, right? So we just use Facebook as an interface, that's all. We have about 10,000 people registered by now. I think this is an old number, probably about 200,000 rounds of games played so far. I think this could possibly actually, benefit from more exposure. So, any possibility to expose it to more people could certainly be very beneficial to collect more data. Again, with 200,000 rounds of games played, we have actually a significantly larger data set than what we could ever collect by paying people. But scaling this up to like a couple of million would of course be even better. We have the data. We will publish it fairly soon. We just can't release it right now yet because of the journal that we're dealing with to publish it, because they don't allow us to publish the data before we publish the paper. So soon we should have the data publicly available for this year. So anyway, so this kind of like solves our trading data problem. So it was kind of like an interesting detour for me, like having focused my entire life on machine learning and optimization and music since about 2005. All of a sudden had to kind of go into this phase of designing a game to collect the data we needed. But after all, this was a very good experiment and certainly allowed us to collect a bunch of interesting data. In fact, I would say that we were even able to do some very interesting things here as well, which I don't know where it's going to pop up in the talk, probably right now. Oh, okay, yeah, so I'll just, I didn't know that I ordered the slide this way. But so basically what I want to say here is that we wanted to somehow check whether the data collected from this game was actually kind of, good quality data. And so what we did is we used the data from the game to train our system, and at the same time we also used a bunch of data that we couldn't mine from Pandora. Again, they don't give out their data, but there are some ways to get some of their data by mining the web. So we use that data to train our system as well, and then test these both systems on our kind of gold standard data, which is the data we collected from human surveys. And so you can see that after a certain amount of time here, after playing the game for a certain amount of time, which is the x-axis, so more to the right means the game has been played for a longer amount of time, you could see that the blue line here, which is the performance of the algorithms trained on the data extracted from the herded game, gets closer and closer to the performance of the algorithm when trained on expert data, basically on Pandora data. So that was certainly a very encouraging evolution, especially seeing that we could get to about 96% of the performance of a system trained on expert data, Pandora data. But what I wanted to say before is that, so one of the nice things of actually developing this game was that, after using the game to just collect a bunch of data, we started realizing, well, if we use the game data to train machine learning systems, then we may actually also be able to to use the machine learning systems to make the games better and make the games collect the data that we're particularly interested in, known in machine learning as active learning, basically. And so we started doing that as well. So we started somehow trying to figure some ways to kind of optimize the game design based on, intermediate estimates of the machine learning models. And what that led to was actually a steeper learning curve. So again, this is the same plot here where the x-axis is time that, the game is played, or basically human effort, like, the amount of time that the game provided. And the yellow curve here is basically a curve that is obtained for collecting data through an active learning loop. So basically we're using the machine learning system, the intermediate estimates of our models, to redesign our games and collect that data that we think would be most useful, feeding it into the models, updating the models, and using the models again to improve the games and collecting better data. And so you can see that in about half the time here, you reach that, performance level that is not significantly different from a system that's trained on Pandora data. So anyways, this was all the kind of like challenges that came with trying to set up, a music tagging system from scratch in the past 4 or 5 years. But now that we have this, there's a couple other interesting things we could do with this here, which we haven't entirely done yet. We are in the process of collecting the data. But basically, one of the interesting things about having a game in Facebook is that you can extract some demographic information about your players. And so it's pretty clear that, rock and roll for grandma is not going to be the same thing as rock and roll for granddaughter, probably. So what we can do is we can extract that demographic information and then use it to personalize the models, basically. Right? So now we can estimate models for the tag rock, but specifically towards, for example, males in Texas or females in Beverly Hills. Right? So that's kind of like a nice side effect, but again, this is data that we're currently collecting. The only thing I can tell you so far that we've noticed is that when it comes to dance music, then females seem to very strongly agree on what dance music is, while males are basically completely disagreeing on what is good music to dance and stuff like that. So we see some interesting effects, but we haven't really kind of like, formally collected all the data and tested these kind of models. But that's certainly one thing we can do here in terms of personalization. However, my personal opinion is that in terms of really personalizing, the music recommendation to people, I think that really the way to go is trying to generate an experience for users where they basically don't have to intervene with the system anymore, and the system just plays for them the music that they would otherwise feel like listening to right now. Basically without telling the system much. I mean, of course, there's always a bit of a cold start loop that you have to go through where users have to indicate a little bit of kind of preferences and provide a little bit of feedback. But basically the idea that we're after here is that the user should no longer have to specify search queries in order to get the playlist that they're interested in. No, these playlists should just start playing at any moment in the day to us automatically without requiring any click interaction. So basically the idea here is, so let's say that it was 10 years ago, this would have been a very hard task, because like how would my laptop know what I'm doing, how I'm feeling, etc., throughout the day? But one of the good things nowadays is that basically everybody pretty much has a smartphone, right? And these smartphones have a whole bunch of sensors in them. And so the idea here now is can we use the sensor signals in this smartphone to somehow figure out what I'm doing or what I'm feeling like, and then immediately serve me the music that I would be interested in listening to. For example, can we use the accelerometer data and GPS data and maybe the microphone data to predict that I'm happy today and that I'm in the gym right now and working out, and therefore would like to listen to some happy rock and roll music. Okay. So this is really ongoing research right now. And so I'm certainly very open to any type of discussing and brainstorming here, but I think that this is really something that's very important to look at, not only for music, but just in general, in terms of providing content to people. You know, again, 10 years ago, somebody going for, you know, to a Yahoo or a Bing search or a Google search, you know, would enter a search query, and personalizing search at the time was probably a hard thing, because it was really hard to figure out what a person was doing or what they were feeling like. But nowadays that people do more and more of these search queries on their smartphones, right? We have a lot more information just from, you know, all the data that the smartphone collects. And it's actually not only just like, you know, by looking at the sensors in the smartphone, but also things like, you know, what did a person just, you know, put on their Facebook status? I mean, it's basically all happening on that phone as well, right? So there's potentially a lot of user information. I know that there's a lot of privacy issues here as well in terms of what information can be accessed. Think about just, you know, for example, having the microphone on all the time to figure out how you're feeling or what you're doing. You may not want that, but at least, you know, if people are willing to opt into it, I think that there could be, you know, a huge amount of benefits here. Now, what's interesting also from the perspective of my group here is that one of the things that one needs to do to kind of address this problem here is analyzing, you know, these sensor signals. For example, analyzing, you know, an accelerometer signal and then somehow try to classify it, right? But what we realize is that we actually have the technology in-house to do this, because an accelerometer signal is in no way very different from a music signal, right? So in the end, what you're trying to do is you're trying to classify one-dimensional signals. And that's how we got very quickly motivated to actually look into this. And so what we're doing right now is we're looking mostly at accelerometer signals and GPS signals. And we would like to look at microphone signals as well, fairly obviously, because this is really just the same thing as tagging music. But this is just kind of like still a little bit challenging nowadays in terms of just bandwidth and collecting the data, as well as, of course, privacy. But so those are the three sensors that we're focusing on nowadays. So for the accelerometer, we're looking at, you know, extracting some time domain features, then the traditional spectral features, and also all kind of like, you know, angular features in terms of how the phone is held with respect to gravity. We're looking at mean, median, variance, and min-max information about the speed that is recorded on the GPS device of the phone after filtering it to, you know, remove some infeasible point, explain the signal and stuff like that. And so we're now trying to classify these type of signals in a fairly similar way as how we try to tag music by using the dynamic texture mixture models, but also looking into just, you know, some kind of more standard techniques like logistic regression and support vector machines to just kind of like, you know, provide a baseline and then see how much, you know, improvement we can get by using these more dynamic techniques. So that's kind of like what we're at right now in terms of trying to classify the sensor signals that are coming out of smartphones for predicting either the activity or the mood of the user. Okay. So one of the challenges that we have here, and again, I don't really know your backgrounds here and or interests, but if this is something that you're interested in or possibly even working on, because I mean, I assume that, you know, this is not a problem that you know, only a few people are looking at it. I assume everybody's kind of like looking at this type of problem, how, you know, smartphones can be used to infer mood and activity of users. One of the big questions that I really have here is in terms of data. So we currently have actually two data streams that we're collecting data from. One is a collaboration with the medical school where they're interested in kind of patient care in general, So the idea here is at a high level that if a patient goes to the doctor asks the patient, like, what have you been up to in the past 2 weeks? And usually most patients have a tendency to talk about what they did in the past 24 hours, right? But not really very accurately about what they did in the past 2 weeks. Like, for example, if it's a patient that had a surgery, goes to the doctor 4 weeks later, the doctor asks, like, hey, have you been moving around a lot? And they'll say, like, yeah, I've been moving around half the day because that's what they did yesterday, but it's not necessarily what they did 2 weeks ago. They may have just been lying in bed for like an entire week and forgot about that, right? So somehow medical people are really interested in this from the perspective of monitoring patients so that doctors don't have to ask the patients anymore, but they just download the information from smartphones. So we're working with some people in the medical school that are collecting search data from like some kind of test group of patients also related to some research that they want to do related to cancer patients. So we're collecting some data from there, and this is going pretty well, but still it's not a huge data set. We also wrote a smartphone app that we're giving to some subjects that we're asking to collect data for us. So people have the phone in their pocket, and now and then the phone will ask them, what are you doing? And then people provide feedback at that point in time. But the problem is, like, if you're actively asking people to collect data, they don't necessarily behave the same way as when you do it passively. Because they're always aware that this phone is there and it's recording stuff, and for example, if you ask them, like, hey, can you just go walking for a while, and then kind of like, record some data for us, then people are very aware of the fact that the phone is here, and they make sure that it, is nicely in the pocket and moves nicely around and stuff like that, which is not always a good reflection of how people will regularly carry their phone or would regularly collect this type of data. So this is still kind of like a little bit challenging. So here I'm certainly kind of very open for discussions if anybody's interested in this here, in terms of how we can collect more useful data for this type of project. But anyway, so the bottom line is we're trying to extract a bunch of sensor signals from a smartphone and then use machine learning techniques to classify these signals into different activity classes and different mood classes of the user. And so basically once we have that, then we can use that to basically drive our search engine and provide the right music to the user. So in some sense we're doing the exact same thing as what we're doing for music here. So now we have a sensor signal. We're basically tagging that sensor signal, now in this case just with emotion tags and usage tags, right? So we have a semantic multinomial that's a little bit shorter because we're just interested in tags of these two specific categories. And then what we want to do is we want to extract songs from a database of songs that match the emotional content and the usage content of what we extracted from the user's activity. Now this by itself can be questioned, right? Because for example, you may be sad, and then what you want to listen to is music that's going to make you happy, right? Things like that. So there's still like a lot of things to be discussed here. In fact, you could even say like, well, why not just tag the sensor signal with the full tag set, as in like, well, for example, given this sensor signal, the user may feel like listening to some romantic music, or the user may feel like listening to some drums music and stuff like that, right? So you could try to do things like that too. So this is type of design decisions that we haven't entirely converged on. But the bottom line really is you have an audio signal, a one-dimensional signal here that you're trying to tag, and then matching of the tags with tags that you have come up with for music signals. And that way you can now provide music recommendations to the user without requiring any active user interaction. So for example, if the user is running around, then you can automatically generate a playlist of energetic music. And if the user is just mellowing out in their couch, let's say, then you can automatically play some very kind of like silent late night music for them. And so again, this is really a lot of ongoing research right now. I don't have a whole ton of results. The only thing I can say is that it seems like by mining accelerometer data and GPS data, you can actually predict user activity up to like 75 to 80% accuracy. So it's actually that there's quite some predictability in there, although if you look at the data, it looks really noisy. But so it seems to be a pretty feasible problem actually. But again, there is from the recommendation and the information retrieval perspective, there's a lot of questions here, right? Again, in terms of like if you discover somebody is happy or sad, then what do you want to listen to? Music that makes them happy, or do they just want to listen to sad music and stay sad? Things like that. So that's kind of like summary of what we're working on. As I said in the beginning of this talk, the idea really is there's a ton of music content out there, and we're going to try to come up with algorithms that serve the right content to the right person at the right time and place. I certainly have to thank a lot of PhD and master students here that have helped me to do all this research. Also a bunch of undergraduate students that helped a lot with building several interfaces. In fact, one of the things that I didn't really mention much about, but so this app here, the Rock My World app, is not just kind of a screen design. This is actually an app that really exists that I developed with two undergraduate students that won the Yahoo hack day 2 years ago. So they came up with this idea of building a music recommendation app that would recommend music location-based. And so this is another component that I haven't really talked about right now. The idea here really is like, you know, I go outside and instead of just kind of searching for music I want to listen to right now, can I find music, say it's romantic jazz music, for example, that will be played in a venue that is within 5 miles of where I am right now tonight, right? I may not find it here, but if I go a little bit south to San Jose or north to San Francisco, then you know you may get a lot of this, hopefully. So we've certainly been very proactive as well in trying to build, you know, apps and interfaces to incorporate these machine learning algorithms. And so really the next stage now is to do this type of recommendation without really having to ask too many questions to the user. So instead of asking them what they want to listen to tonight, they walk outside and you just basically recommend them venues to go to based on what you think they will be interested in to listen to tonight or live venues they would like to go to. All right, so I also want to thank different sponsors that have been helping so far to move this research forward. So that's it. So I'm just like, can I actually ask a question first of all here? So I don't know very much about your background, but like the second half of the talk where I'm kind of like talking about this, you know, trying to predict the mood and the activity of users, is this really like something that's of interest to some of you, or?
Yeah. So I worked in ubiquitous computing and mobile for years now. So a lot of people have, of course, been trying to do this automatic classification of what to do and so on. But I'm just thinking maybe